Hello friends, welcome to the today's video lecture. In the today's lecture, we are going to study there is a relationship between the modulus of elasticity, bulk modulus and modulus of rigidity. In the previous video lecture, we already studied there is a definition and the concept of all the three elastic constants. So all the three elastic constants are applicable only in the elastic region. So let us start the first derivation, that relationship between modulus of elasticity and modulus of rigidity. For that, we have taken one square element ABCD, whose sides are same. Small a is the side of this ABCD element, and it is subjected to pure shearing. And the shear stress is applied in all the four planes. That tau is the shear stress. So after application of the shear stress in all the four planes, so there is a deformed shape. It is mentioned in this particular figure is by the dotted line. So deformed shape due to shear tau, that AEC dash D. This is the deformed shape of this square element because of the shear stress is applied in all the four direction. Drop there is a BD and AC are the diagonal of this square element. So drop a perpendicular BF. So you can see this BF, it is perpendicular drawn to diagonal DE. So diagonal DE is the, because of the shearing there is a deformation taken place. That's why there is a elongation or extension of this diagonal has been taken place. So in this particular figure, BF is drawn, it is a perpendicular to the DE. So let in this figure there is a phi is given. So phi is a shear strain, uh, and capital G is the modulus of rigidity. Mu is the Poisson's ratio, that lateral strain to the linear strain. Now strain in the diagonal. So we want to finding out the diagonal strain. So our diagonal is a BD. If you want to finding out the strain in diagonal, so we have the formula, that is a change in length divided by original length. So you can see this DE minus DF. So there is a total length is DE minus original length is DF. So if you take the subtraction or difference between DE and DF, this is a change in length EF divided by original length is DF. So EF divided by DB, as we know that BD is equal to DF. So because there is a very small angle is there in between, so EF divided by AB root 2. So BD. So BD is already, this is a square element. That's why by Pythagoras theorem, so the sides are A. So BD is a diagonal. So under root of A square plus A square 2A square. So if you take A outside, so A into root 2. So A is nothing but small a is the side of this square element. So this is AB. AB is the side and whose length is small a. So AB root 2. So we put that AB root 2 here, EF divided by. So since the angle of deformation is very small, so we can assume angle BEF is equal to 45 degree. So angle BEF is equal to 45 degree. So though it is at this is the right angle, EBF is the right angle, and the angle of deformation is very small. That's why this BEF angle we have assumed or we consider as 45 degree. And if you finding out that EF value, so EF is equal to BE cos 45. So this is a right angle triangle. So EF you can easily find out. So EF is equal to BE cos 45. So strain in diagonal BD again. So EF divided by BD. So put that EF value, that is BE cos 45 here onto the numerator, and BD already we found that AB root 2. So BE, so again you can find that BE, though this BEA is again right angle, and you can find this tan phi is equal to BE divided by AB. So you will get a tan phi, because the side of this square element is a. So a tan phi into cos 45. So AB means the length of AB is small a, and root 2. So a cancel. Again cos 45 is equal to 1 upon root 2. So it becomes 1 half tan phi. So though it is that phi angle is very small, that's why you can directly take that tan phi is equal to phi. So 1 half phi means phi by 2. So we know that phi is the shear strain, and shear strain is equal to shear stress divided by modulus of rigidity. So this relation we already knows that. So phi is equal to tau divided by g. So phi is equal to tau by g. So this is equation number 1. After that, we know that the above pure shear gives rise to axial tensile stress tau in the diagonal direction of BD, and at the same time, exactly right angle, there is axial compressive stress tau at the right angle, exactly right angle. So the strain along that same diagonal BD, that is epsilon epsilon BD, is equal to 1 divided by E is the modulus of elasticity. So tau axial compressive stress, axial tensile stress minus mu. So there is a lateral compression. So minus mu into again minus because of the axial compressive stress tau, exactly right angle to it. So this formula becomes, and finally the tau divided by E taken common, 1 plus mu. So this is the equation number 2. So again, equate the equation number 1 and equation number 2, because the strain we already found the strain in equation number 1, that strain BD, that tau g divided by g, and 1 half tau divided by g, right? So we already found this. So you just equate both of these equation, and by solving both of these you will get the value of capital G. So by cancellation of the shear stress in both the sides, so it is remaining E divided by 2 1 plus mu, that is remaining. So after simplification you will get this particular formula. So capital E is equal to 2G 1 plus mu. So this formula, after derivation or after finding out the strain in diagonal, so you will get this formula E is equal to 2G 1 plus mu. After that, the relationship between the modulus of elasticity and bulk modulus. So consider a cubic element of side L subjected to stress in the three mutually perpendicular directions. The stress is applied in the same stress is applied in all the three mutually perpendicular direction, that is x, y, and z direction. So your stress is become, if that same or equal stress is applied in all the three directions. So sigma is equal to sigma y is equal to sigma z is equal to sigma. So using generalized Hooke's law, already we have studied that Hooke's law, the strain in x direction because of the tensile strain in x direction. So and in y and z direction there is a compressive strain. Because of that there is a lateral compression. So in the strain in x direction, this is the generalized Hooke's law we already studied. So sigma x divided by E minus mu sigma y divided by E minus mu sigma z divided by E. As the stress sigma causes tensile strain, that is sigma x divided by E in x direction, while sigma y divided by E and sigma z divided by E is the compressive strain in y and z direction. Because of the stress, there is a tensile strain in x direction, while in y and z direction there is a compressive strain. So tensile strain we have taken positive and compressive strain we have taken negative. So uh, strain in x direction, so we know that there is a change in length divided by original length. So though it is a stress is same or equal in all the three directions, so this will become 1 divided by E sigma minus mu sigma minus mu sigma, because in stress in x direction, stress in y direction, and stress in z direction, that all the stress are equal all the three direction. That's why here it is only sigma is taken. So linear strain sigma x is equal to sigma divided by E. It becomes, after simplification, 1 minus twice of mu. So you just called him equation number 1. So as this volumetric strain we already derived that change in length divided plus change in thickness plus change in breadth. So this is strain in x direction, strain in y direction, strain in z direction. Though that same stress is applied, So our stress, same stress is applied in all the three directions. Our strain is also same in all the three directions. So whatever the strain in x direction, we already calculated in equation number 1. So same strain in y direction, sigma divided by e 1 minus twice of mu, and again same strain in z direction also, sigma divided by e 1 minus of twice of mu. So there is a strain, same strain in all the three directions because of the similar stress. But by the deflection of the by the definition of the bulk modulus of elasticity, uh, so we already studied. So there is a deflection, this is not deflection, this is a definition of bulk modulus of elasticity. So k bulk modulus sigma v, that is a direct stress, or because of the identical pressure there is a direct stress divided by volumetric strain. So direct stress sigma, so volumetric strain we already calculated, where this is a summation of sigma x, is epsilon x, epsilon y, and epsilon z. So because of that there is a summation, you will get the total strain, the total volumetric strain in all the three directions. So it is a 3 because of the addition of epsilon x, y, and z. If you take the addition, so you will get 3 sigma divided by e 1 minus of twice of mu. So k becomes e divided by 3 1 minus twice of mu. So e will become 3k 1 minus twice of mu. So this is the equation. As we already knows that e is equal to 2g 1 plus mu, and you just take mu is equal to e divided by 2g minus 1. Put this value of mu in equation number 2. That equation number 2 is here. So if you put that mu value in this equation, that 3k 1 minus of twice, so you put that mu value here, and after simplification, after solving this equation, you will get this formula, which is a relationship between modulus of elasticity, bulk modulus, and modulus of rigidity. 9 kg divided by g plus 3k, relationship between elastic constant. Thank you very much.